Okay, let us begin. My name is Sasha Epanov, and I'm here to introduce our speaker for the final, the third lecture in Della Pietra lecture series. So Della Pietra family is generously sponsoring this series of lectures, and each distinguished speaker invited to speak at those series should give 3 talks. One for general public, and another for high school students, which come here locally from nearest schools by bus. And one more is a more technical colloquium for broader physics and math audience. And our speaker today, I will introduce in a second, but I want to announce also that on Thursday at 1 p.m. the same time here, there will be the Simon Center weekly talk, which is another colloquium talk by Fiona Burnell, and she's going to talk about subsystem symmetry and fractals. Okay, but now let's get to our speaker. Well, I feel weird introducing Cumrun here because probably everybody knows who he is. Cumrun is Holly's professor of mathematics and natural physics in Harvard University. Natural philosophy, right?
It's physics, it's physics.
Philosophy, which is physics.
Yes, that's right.
And he got a lot of distinct prizes, including Dirac Prize and Breakthrough Prize in physics, in fundamental physics. And he's a leader and visionary in string theory and quantum field theory in general. And I hope that you will enjoy the talk today, which is geometric abstractions to scale separation.
Thank you very much. Thanks for the kind introduction. So the talk I'm going to give is related to a couple of works we have been doing in the past few months with different collaborators, Collins, Jeffries, Chu Yao, and Luslan Wiesner and Chu, and some work in progress with Montero and Valenzuela. The presentation I'm going to be doing is not so much like a colloquium style, I'm afraid, so it's not going to be like a review of a broad range of things, and perhaps that's what I should have done. Maybe I misjudged the nature of the seminar. It's more technical than that. So now, since I see some of the more broader audience in this one, I try to describe some other aspects of the issue, so it's not as focused as a very specific thing here. So that's a bit more relevant for some more general discussion. So the thing I want to describe is recent work we have been doing in the context of trying to understand solution in the context of string theory and quantum gravity more generally, and considering the type of solutions we are interested in, the homogeneous solutions. And there are 3 types. We can have Minkowski, they're missing here, Minkowski, ADS, and de Sitter. And well, the Minkowski solution, if you think about if you have some fields that's parameterized, let's say your vacua, the potential in the case of Minkowski should not depend on it. It should be 0, in fact. And that's the Minkowski solution. And in the case of the ADS, the minimum should appear for some range of these moduli to be frozen at some value, which is some negative value. So that's what we call, that gives rise to ADS solution. And the positive potentials will give you de Sitter solutions. All the examples we know of and various general thoughts suggest that no matter what you do, the potential approaches 0 exponentially fast, far away in field space, so always asymptotes to 0. And so in the context of the de Sitter, at best you might have a metastable situation because there's always something lower in energy farther down. So that's the general solution. And we don't even know whether or not there is a metastable de Sitter or not. And there are question marks about whether this can be realized or not. The case of ADS is an example. It's a case where we have a huge number of examples, specifically for supersymmetric situations. Again, if you break supersymmetry, there are ADS solutions, but we expect them to be unstable one way or another. So these kind of compactifications come from some internal manifold with times Minkowski, or internal times ADS, and internal times de Sitter. And in the context of Minkowski space, the size of this manifold is uncorrelated with the size of Minkowski. In fact, there is no size in Minkowski. There's no scale associated with it. So it had to be decoupled, and it is. In other words, you can choose typically any size you want. For example, if you have a Calabi-Yau manifold, you choose any size Calabi-Yau. There's nothing which constrains the length scale of Calabi-Yau relative to the Minkowski space, because there is no scale in Minkowski. But ADS and de Sitter have a length scale because there's a curvature. And you can ask, given that curvature scale of the sitter, whether or not there is any relation between that length scale and the length scale of the internal manifold. Do the lengths have to be comparable, or can you decouple them? So this is the main question, whether or not the length scale associated to these spaces are decoupled or not. In the context of the ADS, there are many solutions, as I mentioned, but it turned out that you cannot decouple the relation. There's always a relation, seems to be, between the length scale in ADS, as measured, let's say, in Planck units, compared to length scale in the internal manifold. And essentially, all the examples we really understand correspond to giving you, there's a piece of the internal manifold whose length scales the same way as ADS. So when you want to make the ADS to be bigger and bigger, you end up getting at least part of the diameter of the internal space to be bigger and bigger in the same rate. There's a conjecture suggesting that if there is not equal to 1, then the value of it should be bigger than or equal to 1. And this has some meaning in the context of the conformal field theory dual to these holographically dual to these anti-de Sitter spaces. So this, as usual, the holography suggests that the ADS is related to a conformal field theory dual, in which case the scale of the conformal dimension of the operators is given in terms of the mass of particles in the bulk.
If it's not 1, what makes this ratios dimensionless?
There's a Planck I'm not putting in this discussion. Yes, I should have put M Planck somewhere. So yeah, so if you compute the conformal dimension, then you have LADS. Or if M is like 1 over LK, then this will be the dimension, and then you can get some scaling depending on what's the power of A. So if A is of order 1, you get dimensions of order 1, conformal dimensions of order 1. If A was less than 1, we get dimensions much larger than 1 in the limit of large ADS radius. So the case that we have control in quantum gravity is when you have large L, which means small curvature in ADS. And in that context, that will give rise to, if you had A less than 1, to get bigger and bigger dimensions of the operators. Now, this is actually quite interesting, because if you could do that, if you could indeed find large ADS solutions for which the scale of the internal manifold is decoupled enough, like in the A is less than 1 in some form, then there's sufficiently decoupled, that is, you need to do, but not necessarily. So suppose that, for example, there is no relation between ADS scale and the internal space. Then it's easy, potentially, to perturb it by adding some extra ingredient to break the supersymmetry and push the energy up and get this other solution. So it's very naturally connected to the question of whether you can get de Sitter or not easily. But this is a better, easier, or a more accessible question, because now we have techniques of holography and conformal field theory to bear on this question before we get to the more murky situation of what is the story with de Sitter, which is much more complicated, it seems. So this is a good ground. The ADS part is a good ground to actually explore, to see what are the possibilities of coupling of these scales together. Are there a relation between them, or can we decouple them? Now, what do we know about the dimensions of operators in conformal field theories? Well, in d-dimensional space, if you have a space-time, if you take an operator of conformal dimension delta, if the delta is less than or equal to d, we call this relevant or marginal operator. And if the dimension is bigger than d, we call them irrelevant. No conformal field theory in no dimension is known to have no low-lying conformal operators. In fact, the biggest gap we have found in any conformal theory is in 4 dimensions, and that's the monstrous moonshine construction, for which the gap can be made as big as 4. That's it. There's no stronger. Yes? Sorry?
It's 2.
No, conformal dimension is L0 plus L0 bar. It's 4.
Oh.
Yes, you're talking about spin. Yeah, I'm talking about dimension here. So no conformal field theory is known to have gap. So this is, in other words, this is, in the usual language, is irrelevant operator, the first operator. It's dimension 4, not 2. So no operator is known to, no conformal field theory is known to have a gap bigger than that. That's surprising. Now, you could say, well, these are very hard to get, possibly, but it's surprising that despite all these efforts for all these years, even in 2 dimensions, which we know a lot about conformal field theories, Not a single example is known with gap bigger than 4. Now, question is, well, could it be that we have not been smart enough to construct these solutions, and maybe there are something? Could there be a CFD even? Maybe there are some CFDs which have a few low-lying operators, and then a big gap, and then some other stuff. Could that be like that? Could we have such stories? Again, none is known. So we can start to ask this question in the context of holography. What would this question translate to in the holographic language? In the context of holographic language, if you're interested in the gap, the natural question is related to whether or not there's a KK tower of states and how do they scale, what are their masses. In other words, if we focus on massive spin-2 operators, not the arbitrary conformal operators, but massive spin-2 operators, then that will give you a specific class of conformal operators in the dual theory. And if that has a big gap, that means you have squeezed the internal manifold in a tiny bit. So in other words, we don't need to know about, there might be some low-lying states, but if the internal manifold is sufficiently small, just like in Calabi-Yau case, the KK modes can push it up. So we can ask that question. So could it be that the spin-2 operators, the first spin-2 operators, can be made very massive while some other low-lying ones are light? That's a more natural question to ask for scale separation. So that's the one we are going to ask. Not necessarily that there's no conformal operator, but what is the first spin-2 operator? And the relation between that is in the eigenvalues of scalar Laplacian come into play here. So the conformal dimension of the operators in D dimension, if they're delta, they satisfy a relation like this, where lambda is an eigenvalue of Laplacian and A is some order 1 number, depending on which problem we are trying to solve exactly. So basically, the question of how big delta can be boils down to studying the spectrum of scalar Laplacian on these manifolds. So if we consider holographic cases where branes probe singularities of internal manifolds, the corresponding holographic setup is particularly nice and simple. You take ADS times some internal manifold, and K is an Einstein manifold. Einstein manifold satisfies an equation of the form that the Ricci curvature is proportional to the metric, and we normalize the metric so that it's in this particular normalization in dimension n. I'm taking n to be the dimension of K. And to get an ADS, you need this Ricci curvature to involve positive curvature to give you negative ADS curvature down here. So we have positive curvature Einstein manifold satisfying such an equation. This is the leading equation that you get for the limit of large K or large ADS. So we can start with this as a good approximation to our system and ask, suppose you have a manifold satisfying this. What is the scalar Laplacian on spectrum of scalar Laplacian on this kind of manifold where you have normalized the metric to be this? Can you make the scalar Laplacian to have a bigger and bigger gap with this condition? That's the mathematical question we're asking. Well, let's consider a simple case. Suppose you take K to be n-dimensional sphere. Naively, there seems to be, should be possible, it seems, because you naively might think, look, take a sphere, quotiented by a group, discrete isometry of the sphere, a subgroup of SOM plus 1, and squeeze it to death, so to speak. You shrink the sphere by quotient a lot. The volume certainly can be made arbitrarily small. And one might think that, well, that means that if the volume shrinks, the length shrinks accordingly by the order of the group to the 1 over nth power as g goes to infinity. So one might conclude from this picture that the first eigenvalue will scale like 1 over this length, which therefore can go to, so the eigenvalue could be arbitrarily made large by taking g to be arbitrarily large order. This turns out to be false. And it's very instructive why it turns out to be false, because you might, without any thinking, this is the kind of order of magnitude that we might have naively believed in physics. And in many papers, not exactly on this problem, similar problems, one would naively say, oh yeah, this is the right order, the size is of this, and this is the answer. And this is incorrect. This badly fails. And it's instructive, and many of the heuristic arguments we unfortunately see in the physics literature involve this kind of heuristics kind of assumptions, which are not valid. But let's just figure out what went wrong with this picture here. What went wrong is the following. Our intuition is like, suppose you take a huge regular sphere and model it by Zn, so you can make it arbitrarily thin sphere. And then, so you can say, okay, I've shrunk this to nothing, but actually not really. The diameter is still the same as before. You haven't shrunk the diameter even 1 bit by Zn. So you say, oh, what else can I do? Well, all I can do is just exchange up and down, and that's it. You don't have much more choice if you do Zn, and you can only take up and down, and that only halves the diameter further, nothing else. So this shows that doing this is not very smart in some sense. You do not decrease the diameter too much. So you can then ask, suppose I did this problem for different spheres in different dimensions. What would the answer be? Not 2 sphere, any dimensions. Take 3 sphere. The first eigenvalue for the round sphere starts with 3, the first non-zero eigenvalue. And then it can be made pushed up to even as big as 168. So you can make the scalar Laplacian pushed all the way up to 168 for the eigenvalue, for the Laplacian. And this corresponds to the dimension of the first spin operator being pushed up from 3 all the way to 14. The diameter can be, in other words, shrunk down from pi to 0.32. That's how much you can shrink the diameter in this language for the sphere. Which one achieves that? Well, it turns out that if you think about the S3 as having an SO4 isometry group, if you take an SU2 diagonally embedded in SU2 left times SU2 right identified with the SO4 of S3, if you identify that and use the icosahedral group, that's the same one which gives you the famous E8 in the SU2 case. That's the one which achieves this smallest diameter or biggest eigenvalue, 168. So this is showing that opposite to our intuition, it's not the one which with more elements which does the job. It's the exceptional one. And there are only a few exceptional ones we can only have. The finite exceptional ones are the best in trying to push the eigenvalues up or diameter small. And that's the lesson we learned from this example here. And for the case of the 5 sphere, again, we can do a similar thing, and you find the eigenvalues. The diameter can be pushed down from diameter pi, which was the original diameter, all the way down to 0.96. And the delta 1, the first spin 2 operator, the first non-zero spin 2 operator goes from 5 up to 8. And then for the case of the 7 sphere, you can again do the same thing and push it a little bit, 3.5 to 5. Again, all of these are somehow related to the icosahedral group in different forms. Now, you might say, OK, so we have done a few examples. And you might ask, wait a second. Is it true for non-supersymmetric orbifolds? Is it true for the ones which have fixed point? Is it true for all spheres and all that? The answer is true for all spheres, irregardless of whether or not you have preserved any kind of supersymmetry in any dimension, or you have fixed points or not. There is the minimum diameter you cannot achieve any better in any dimension. Of course, the minimum depends on the dimension, but for any dimension, there is a minimum. And you cannot do any better. You cannot push it down further than that. So this you can prove, and this is what we proved in our paper. It's just basically some group theory statement that you can use to show this. OK.
Because everywhere it coincides, lambda 1 equals delta 1 log, and then for S7 it's 3.5.
Yeah, it is correct. This one is the correct one.
Cumrun?
Yes.
So let's substitute n equals 1 in these spheres. So this is a system that you know very well.
N is the one, S1 you mean?
Yeah, so
there you can, of course.
make it smaller, but then something else happens that you know.
Winding one.
The winding
You're right.
come down. So the statement about just the eigenvalues of the Laplacian cannot be as strong as you stated. Maybe you have to assume that n.
Right. So let me remind what was the basic premise. The premise was that we have ADS. ADS needs a positively curved space. S1 does not have positive curved space. So I specifically need all the spheres with positive curvature, not S1. So that I should have said the positive curved spheres. Not S1 is not positive curve, and that's why there's an exception.
No, but there is a solution of ADS 5 times S1 if you add flavor to it.
In other words, you can have S1s as part of it, but you certainly need an additional piece. For example, you can have ADS 3 times S3 times K3, or ADS. So you need something else. I'm talking about that something else, which has positive curvature. That's positive curvature part, because not all of the parts of the internal manifold will grow at the same rate. So I'm talking about only the piece that is positively curved. So you could say, okay, I'm being blindsided by looking at these stupid spheres. We should look at much more general examples. Let's try our hands a little bit more examples. You can study 4D conformal theories with n equals to 1. 4D n equals to 1 conformal theories are an interesting class. And how do you get them? Well, you can take D3 branes probing Calabi-Yau threefold singularities. There's a huge number of Calabi-Yau threefold singularities. Pick one, put the D3 brane, and study that conformal field theory and see what kind of operators you get and what gaps you get. Well, if you do those, for example, you take a Calabi-Yau singularity of the form, let's say Fermat type, Zi to the AI equal to 0. Put a D3 brane probing this singularity. It turns out that the biggest gap for holomorphic eigenvalues correspond to the exponents 2, 3, 11, and 13. And the dimension of the spin operator, sorry, I should be more precise. Here I'm not looking at the spectrum of the Laplacian only, because that's going to be very hard to find all the eigenvalues, because we don't even know the metric of the corresponding space. So let me explain better. So what happens here, if you put the D brane probing this singularity, what you end up getting is the Calabi-Yau actually basically gets what's called the cone over the Sasaki-Einstein manifold. The Sasaki-Einstein manifold, which is a 5-dimensional space, is the space I'm talking about when we're talking about the ADS correspondence. So you have ADS 5 times the Sasaki-Einstein manifold. We don't know the exact metric on the Sasaki-Einstein manifold, so we cannot compute the Laplacians generally. However, for holomorphic eigenvalues, we can. And this is related to the fact that we have non-renormalization theorems and so on in the context of n equals to 1 4D language. So for those you can. And that's if you want to find an upper bound for the dimension of operators, it suffices to put an upper bound on the holomorphic ones. Because, yeah, the holomorphic one is good enough to show there is a bound. So for the holomorphic spin-2 operator, the biggest, in other words, for the holomorphic in this language means chiral spin-2 operators in 4D n equals to 1, the biggest bound, you can push the bound all the way up to 202 of the dimension. So it's pushed it up. Again, I emphasize this does not mean you don't have lower eigenvalues. I don't claim that there's this much gap in the whole spectrum, but this is the gap if you restrict to chiral operators of spin-2.
Conformal index that would begin only at that order, no? Because there are conformal, superconformal.
Yeah, there's at least here. There's at least, exactly. So you can.
Superconformal index.
They may have done it for, I don't know if they have done it specifically for this class or not, but if they have done, they would have seen this. This is the biggest one you can push it up to. And this is actually, you might actually notice a similarity here. You see 2, 3, it reminds you perhaps of 2, 3, 5 of E8. And this is not accident. In fact, you can actually, this is an extension of the E8 singularity becomes this as the most special one. So just the same role that the E8 singularity played in putting the biggest eigenvalue, pushing it up all the highest possible one, is being played by this special one. You can do a similar game for M2 branes probing Calabi-Yau fourfolds. And in this case, you get 3D n equal to 2 theories. And again, you can ask if you restrict to Fermat type, what is going to be the biggest exponent? And you get the exponent to be 2, 3, 7, 83, and 85 to give you the biggest holomorphic eigenvalue for the scalar Laplacian. And that corresponds to an operator with dimension 6,975. Yes?
Because there are S waves also. So there will be chiral primers which are very low lying. And then you can
We're talking about spin. I'm not talking about all the chiral operator. I'm talking about the ones coming from scalar Laplacian only. There are other operators maybe.
What's the statement in field theory? You can make products of big operators.
There might be other operators that I'm not saying that. So let me be more clear. I'm not saying that in this theory there are no other chiral operators with lower one. At least these give you the gap.
I think is only the single trace operator. There's an implicit large n here. Otherwise, of course, we can get product of stress tensors.
No, stress tensor is not BPS, but there are some low-lying not BPS operators.
But this whole talk is predicated on just counting the single trace operators.
I'm talking about the chiral operators, which would correspond to, in the language of holography, would be single trace operators, which are the eigenstates of these guys. And again, I emphasize, I'm not saying that these are the only eigenvalues. I'm just focusing on a eigenvalue because I just want to put the upper bound. If I want to put an upper bound, I have to find one. I don't care about everything else. So there's an upper bound. This cannot be any more than this. Now, these theories will have other operators, which is not coming from scalar Laplacian, because there are other forms and all that. You have to study the spectrum of those guys. I'm not studying it. So in the full 4D theory, there'll be other stuff I'm not talking about. This is only coming from scalar Laplacian specifically. But anyhow, the thing I'm trying to emphasize here is that these are computable numbers. They look like big numbers, and they are really like extensions of E8. They're special, somewhat like E8, 2, 3, 11, so 2, 3, 7, 5. In fact, you can ask this kind of question in a more general setup, and for any n dimension, a Fermat type, what is the biggest eigenvalue you can make for the corresponding holomorphic one? And you find the pattern like there's a formula. You can actually find the general formula of how these coefficients grow, the powers grow. You start with 2, and then 3, and then so on. There's this product structure. Actually, this is amusing because it relates to a statement about conformal field theories in 2 dimensions as well, which I don't know how to prove. And this is related to the following. If you say, OK, I have this conformal theory, what does the wordsheet see if you have the wordsheet theory? You can say that maybe it's not even geometrical, and I'm just talking about the background in the 2D wordsheet. So in the 2D worksheet, what typically happens is that you get a linear dilaton direction together with a conformal field theory as a product to give you basically the full dimensions that you're looking for. And so typically the structure that you will get will be, let's say, in the context of Calabi-Yau, a 2-2 superconformal field theory. And you'll be looking for theories which have c hat less than n, where n is an integer. And you're looking for the lightest chiral operators in the 2D language. And the statement is that if you take if you fix an integer n, and if you take any sequence of conformal theories approaching n, c hats, the central charges approaching n, if you take the ratio of q divided by the deficit of n minus c hat, it's bounded by a universal constant independent of conformal field theory, and only depending on the dimension n that you're interested in. And you can check this statement. Of course, in all the examples we know it's true, but I don't have a proof of this. But this kind of question raises this as a potential conjecture for 2D CFDs with n equal to 2 supersymmetry, 2, 2 supersymmetry. This translates to the conditions I was saying. If you're saying that, well, maybe I have a geometry which is nothing to do with Calabi-Yau or anything, what about this? And this is the kind of answer you would be getting in the context of string wordsheet. So in fact, we have shown that for arbitrary, not just Fermat type, arbitrary regular singularities of Calabi-Yau threefold, which have been classified by Yau and collaborators, we have shown that for all of them, there's a universal upper bound on the first eigenvalue of the scalar Laplacian. And therefore, there is an upper bound, period, for all these Calabi-Yaus of this type. The irregular singularities have not been fully classified, but to the extent that they have been studied, again, they satisfy this property. And if there are finite number of types of irregular singularities, then we can prove that for each type there's a finite upper bound. So this idea that you can push this upper higher and higher does not seem to be possible. So based on all these examples, we make the following mathematical conjecture. The diameter of an n-dimensional positively curved Einstein manifold is bounded from below, and the first non-vanishing eigenvalue of scalar Laplacian bounded from above, where the bound depends only on the dimension of the manifold n. This statement seems to me sufficiently simply stated in some form, and one would have thought that we already know the answer to this. Say, for example, for the Einstein manifold, we don't know. And it's surprising that such a general statement could potentially be true, and nobody knows either a counterexample or a proof of it. So this I find remarkable. So that's the conjecture we are making, mathematical conjecture. This conjecture would translate to the scale separation that I was talking about in the context, the geometric obstruction to the scale separation. This would be the geometric obstruction. In the specific case where the internal manifold K has something to do with Einstein manifolds. Now, this would be the case, Einstein manifold would be the case if only we have, brain probing singularities. But of course, in string theory, we can have other ingredients like fluxes of different types and this and that, which is not just a single brain. So this does not prove, even if you prove the statement, even if this is true and it's proven, it doesn't prove that there is no scale separation, but at least it goes in that direction. There are examples in the literature, notably the DGKT example, which would lead to a situation where you do have some kind of a scale separation if the construction is correct. Now, first of all, there are problems with the construction because you have singularities of these geometries construction which have not been fully resolved. For example, you have intersections of orientifold planes and so on. which people are still debating what is the status of them. But there are some examples like DGKT that recently were studied. Examples in the context of DGKT, DGKT does not correspond to the Einstein manifold because they have other ingredients. But there are examples of it which in the work of Cribiori et al., they added some extra fluxes and get rid of some extra flux. In the same philosophy as DGKT, they managed to dualize and get it back to an M theory with pure geometry description, which involves the pure Einstein manifold. So they will get an ADS4 times the pure Einstein manifold in 7 dimensions, as it would be equivalent to DGKT, with the same kind of predictions as would be the DGKT. And in that context, we believe that the statement is that that manifold does not have the correct diameter as they are predicting. And their argument is heuristic because they are doing these scalings that, as I tried to explain in the case of a sphere, misleads us. And they, of course, they do not have the precise metric, so they don't know. They're just making a guess.
DGKT?
This is a construction in the context of type 2A, ADS4 times some Calabi-Yau orientifolds, and you add ingredients like D0, the flux corresponding to Roman's mass, and F2, F4, etc. So in the context of type 2A. So people have talked about it. And then there are issues with orientifolds intersecting and whether that's actually under control and all that. But the basic guts of it is that you have one integer flux, which is the D4 brane flux, which can be made arbitrarily large. And you can then try to check with respect to that rescaling whether or not you can get a scale separation. And the claim is that in that case, the scale of the internal manifold does not grow as fast. It goes slightly lower. It still grows as you increase the ADS size, but slightly lower than the scale of the ADS. That's the claim. And that's what we are debating, whether that's possible or not. In fact, the DGKT has other problems, regardless of this other one. The other problem is that if you rescale that n, the number of the F4 flux, so to speak, the number of degrees, the central charge of the conformal theory goes like n to the 9/2. By rescaling, that's one flux. Now, in no example we know of in the context of branes, you have a situation where a single brane, which you grow that by a factor of n, goes faster than n cubed. The highest we have is the 6D theories, which give you n cubed. So these go like n to the 9/2, 4.5. So that's already way too big compared to any branes we know. So this would be quite remarkable if there is such branes. Yes?
Getting an Einstein manifold from Kähler manifolds in general, right? You only consider from Calabi-Yau getting an Einstein.
You can have any examples of Einstein. So I was just giving you Calabi-Yau examples. In fact, for the Kähler-Einstein manifold, there's a relatively simpler argument, certainly for the smooth ones, because the fact that they relate to first Chern class, and the first Chern class is integral, gives you a bound immediately. So it's much easier proof. At least for non-singular ones, for which the first Chern class is integer and so on. Okay, so this is
DGKT stands for what names?
De Wolf. What are the names?
And I don't know G.
Okay, anyhow, so it's such a well-known construction. People always get DGKT. I don't remind myself everybody who the DGKT are.
And I'm a bit confused about the conjecture. You said Einstein manifold.
Yes.
In the case of Ricci curvature zero.
The what?
Ricci curvature zero.
No, this is not Einstein positive curvature.
Positive.
Positive Einstein. Yeah, I think that's related to the issue that Natty was also raising. For the circle, there's a counterexample. Easy counterexample, the circle.
You make it now kind of curvature 1 or something.
Yeah, the curvature. So we normalize it very specifically by this. I just chose the usual one, like a round sphere case. So for this one, the claim is that the diameter cannot be made arbitrarily small. There's a lower bound on the diameter, which is depending only on the dimension.
So in this M theory presumed example, so you know the ingredients, and one would just have to construct the metric on this manifold, and then
Yes.
like really such a
Yes. The statement would be that if our conjecture is true, which in Einstein manifold doesn't happen, which I think we have strong evidence, we would say that's not possible. The arguments that suggest that's otherwise is heuristic. They don't really go to the level. They don't have as much. They cannot go as much as trying to say, oh, this is the metric, it's a good approximation. Let's compute the diameter. They don't.
Maybe it's literally a problem. There's no war.
No, there's no. It's just ADS4 times the 7 manifold. So
War can change any of your concepts.
I think there's presumably there's a warped version of these, but we haven't studied that, so let me not say it. Oh, here, sorry. So,
what is the connection between the conjecture about the gap, that it cannot be too large, and the absence of the Sitter Vafa? I didn't understand.
Okay, so the idea is that, so let me take the extreme case. Suppose the gap can be infinitely made large. This is not. So suppose you take a potential which is arbitrarily close to zero, with big gap of these states. A little perturbation does not. You don't need to know about the details of the internal one because they're all so massive. So a little perturbation will push it up. Whereas if you had these other modes, this little perturbation could mess it up by some Susy breaking term. So in other words, if you're at the verge of crossing zero potential with nothing massless around, with nothing very light around, then you have an easy chance of lifting and getting the sitter. So this is closely related. And in fact, all the attempts of KKLT and other ones are pushing exactly that button, trying to get close to the ADS and then pushing it a little bit up. So it's a key issue, and this is, I think, I want to attract the attention of our community to this problem because the ADS is potentially something we can say precisely, rigorously something about.
As you've shown, the potential always goes to zero at infinity, so you're always going to deal with light moduli in that limit.
So if you're far away, you will have to. The hope, for example, in the KKLT is that you will push this enough up without changing that. You just get a little bump. So I'm not going to defend that, but that's basically the hope. I'm not saying this even if you achieve it's automatic, but I'm just saying that's the hope. But you'll be much more problematic if you have these light states. So having these light states gives you basically you lose control.
Sorry, in this ADS 4 times in MC example times whatever 7-dimensional mechanism, you have a whole one parameter family level by n.
Yes. Same story as the DGKT. So this is basically a DGKT-like solution with the same logic. In that case, that n which parameterizes gives you the central charge going like n to the 3/2, which is much more respectable. So that could even look very reasonable from that viewpoint, but then it has this other issue. Oh, so let me come to the holographic obstruction to KKLT. So KKLT is for those who are not perhaps very familiar with the story here, is one of the very few suggestions of scenarios where you can realize de Sitter in a controllable fashion in the context of string theory vacua. And it involves two steps. First step is to use type 2B orientifold or F theory on elliptic Calabi-Yau 4-folds, or type 2B orientifold on Calabi-Yau 3-folds, or F theory on Calabi-Yau 4-folds. And in addition with the flux, to obtain supersymmetric ADS with small cosmological constants. Very much along the same line of what we were talking about, except different kind of backgrounds. To get a small negative cosmological constant and ADS. You want to make a big radius ADS or small cosmological constant. And the step 2 is to add anti-D3 branes at highly warped parts of geometry to uplift the energy to positive cosmological constant, leading to de Sitter. This is the basic idea steps. And now the step 2 is harder to analyze. As I said, you break supersymmetry. You have all hell breaks loose. You have no idea what to do. But this one, it is supersymmetric, so we have at least a chance of trying to get somewhere. Now, the point of the rest of the talk is to argue why step 1 cannot be realized in a controllable fashion. So the step 1, which is supposed to be the easy step of KKLT. So let me review it. You start with the KKLT in the following form. Let's say the easiest form of it, let me say, well, you can have it different forms, but if you take F theory on elliptic Calabi-Yau 4-folds or Calabi-Yau 3 orientifold, which are equivalent to the 4-fold version by multiplying by an extra 2 torus and modding out by an extra Z2, there is a tadpole condition, and this plays a key role in the whole discussion, which tells you that you cannot, that there is a relation between the Euler characteristics of the Calabi-Yau and the fluxes that you have to turn on for the Ramond, and Neveu-Short's 3-form fields, as well as the number of D3 branes that you have to add to the game, such that this sum is bounded by the Euler characteristic of the Calabi-Yau. So this already tells you that you're going to be having a finite list. The biggest Euler characteristic we get for a Calabi-Yau 4-fold is around 1 million. So you're getting fluxes which are bounded, whose square is bounded by 1,000,000. So you're talking about flux quanta of order 1,000 at most in this discussion. So you're basically talking about the flux of orders 1,000, which correspond to presumably brains, thousands of brains, to try to get a huge ADS. This already should bother us, because it sounds like trying to get, just to give you an analogy, suppose you take orientifolds, and suppose you want to get SO 10,000, n equals to 4 Yang mills in 4 dimensions, coupled to gravity. Well, you take T6, you orientifold it, well, you can just find some finite number of orientifold charges, you have to cancel, that's all, SO32 or something like that, not SO 10 billion. This is somewhat like that. These are exactly or analogous to the same thing as the background charge you need to cancel, which means, yes, you can, by choosing a Calabi curvature, you can introduce extra brains, but not that many. KKLT is hoping, out of these few brains, to achieve a large ADS, a huge central charge. Bizarre. Already we should say, what? This sounds strange. Supersymmetry and all that will give, you can try to break supersymmetry and all that by putting negative brains and so on. We're talking about preserving supersymmetry. So I should emphasize, maybe I didn't. Yeah, I did say it. So they're talking about supersymmetric ADS vacua. Supersymmetric ADS vacua is the only thing I'm going to talk about, and that was the first step, because you want to have control over what you're doing. So that's the first step. So in that context, you have positive quantities adding up to this. So the best you can have is to have no D3 brain, put all of the fluxes here, and hope for the best. The highest known Calabi fourfold, highest known that people have constructed up to now, after 20 years or so.
But it's not an in principle.
It's not in. But I will show so I will argue later that even if it's arbitrarily large, there's a problem. So there's a problem regardless. But here I was trying to say in what we actually know. So in the cases that we actually know, the highest one is 1,000,000, which is a flux number of order 1,000. And one is trying to get the central charge, people say, of 10 to the 100. It just doesn't go that way.
Which says there are finitely many of the Calabi.
Well, these are all conjectures. These are all conjectures. These are all conjectures. We don't have a proof, but yes, Yao has conjectured that, we have said it, and so on. Other people have said. There's conjectures, but Zohar is saying we don't know that. That's true. We don't know that. We're just conjecturing. But there's strong evidence that this may be true. So you have this formula that this is the language that you can do it, and you can also relate it to this the fact that the Euler characteristic of Calabi fourfold in the language of type 2b is the number of orientifold O3 planes that you have, plus the Euler characteristic of the O7 planes, orientifold 7 planes, with these relations of 4 and 24. Anyhow, you can relate in different forms. So as I said, we want to probably make this zero for getting mileage out of this as much as we can. So this leads to effective 4D theory to leading order, something like this, where W is G wedge omega, where the four-form flux. So I'm now using the F theory language translated to the M theory language. So I'm bypassing discussion here, but as if I'm going one dimension low. So as if I'm talking about ADS3 situation, which is similar. Again, the KKLT logic would also go through in that case. So let me pretend like it's like that. And you get a W, which is G wedge omega. You can, of course, retranslate that in type 2b language. And in type 2b language, this is what you will get in the orientifold language, for example, where G is the combination of the Ramond, and Navier-Stokes free-form flux coupled with the coupling constant of type 2b. If we define a quantity, which is the norm of W times e to the k over 2, then ADS vacua, where we look for DIW equal to 0 or W not equal to 0, is equivalent just to critical points of this Z. This is not just simple algebra. It's nothing fancy. So you can recast finding ADS vacua as finding critical points of this function. And this looks like an attractor equation. This is actually pointed out by Svietek et al. And also by Kallosh herself in papers, where they noticed that, in fact, this appeared also after KKLT paper, that, finding the critical points of this thing sounds very much, ADS vacua is very much like attractor equation, but it wasn't connected to attractor of what? what are you solving the attractor equation for? But actually, that corresponding question was asked by Svieti et al. Already in '92, and that's what I'm going to review. But before I do that, let me remind you the versions of attractor, which is somewhat similar to this, which we are more familiar with. Take type 2B on Calabi-Yau threefold, and consider D3 being wrapped around 3 cycles. That gives you black holes. In that context, we have an attractor equation, which is the following. You consider the quantity which is the mass of the D3 brane in Einstein frame, which is the integral of the holomorphic 3 form over that cycle, normalized so that the volume is corresponding, the volume is 1. This gives you the mass of the black hole. And the attractor flow means you want to minimize the mass of the black hole by going to a point in moduli of Calabi-Yau such that this is as small as possible. And this is the attractor mechanism in the usual Calabi-Yau case. And this looks exactly the same kind of logic as this one. So again, let's go back to our problem, though. We can, in principle, consider ADS in 4D or 3D. As I just said, F theory on elliptic fourfold or M theory on Calabi-Yau fourfold. Now, the statistical arguments for KKLT would apply equally well to both cases. So if it doesn't work in one, why should it work the other, and so on. The 3D case we can say more about because it's purely geometric. Now we're talking about just M theory on Calabi-Yau fourfold. How do we interpret the attractor equation? Well, if you replace the fluxes by branes, what are the fluxes? You have a G4, you just have to replace by M5 branes wrapping around 4 cycles. Condition for supersymmetry requires it to be special Lagrangian. So the Kähler class vanishes on it, as well as the imaginary part of the holomorphic 4 form, suitably with a suitable phase in front, should be 0, should be purely real. These are what we call special Lagrangian submanifolds of the Calabi-Yau fourfold. So finding the tension is basically trying to find the minimum tension of exactly this object, which is like the usual attractor equation. In fact, this is the kind of the picture coming from the work of Svieti et al. If you put a brane here, then what you find is that the flux that it generates can be viewed as trying to generate a ADS vacuum to the right of it, with the flow of attractor flow, which gets stopped precisely when you get to critical points of Z. So you will put a brane here, and then you generate the brane here. So this is, of course, a little different from the usual attractor mechanism, because the attractor usually is at the brane itself. Here, the brane, that in this case is codimension only 1, only generates the ADS to its right with these properties. But otherwise, it's very similar to what we usually talk attractor mechanism. And therefore, if we have KKLT realizing ADS, and we expect there to be a holographic dual for large radius ADS, then the object here, there is a 1 plus 1 dimensional domain wall in 3 dimension, should do the job. M5 brane wrapped around 4 cycles, has the right supersymmetry, has the right flux. Therefore, it generates the corresponding geometry. You just count the degrees of freedom on this guy to see what are the degrees of freedom of the dual theory. So basically now this is, if you ask in the context of type 2B language what this means, in the context of type 2B language, this M5 brane gets pushed up to D5 and NS5 branes, wrapped around cycles of Calabi-Yau, and then now wrapped around 3 cycles of Calabi-Yau with a 2 plus 1 dimensional domain wall in 4 dimensions. Again, they would lead to ADS4 vacuum exactly the same way. Now, the scale of ADS vacuum, the size of ADS length scale associated with ADS squared is related to the central charge for the combination of D5 and S5 brane, which give you the right flux. Or in the context of M theory, the L of ADS is corresponding to first power, is corresponding to the central charge. What we're going to basically argue is that the central charge of these theories is less than the Euler axis of Calabi-Yau. That's all, which is not shocking after all. It's not shocking because Calabi-Yau was bounding the number of flux you could put in. So this is not at all outrageous. It's just saying, OK, you have a certain amount of flux you have around, put them in and see what you get, and this gives you a bound. That's all. So here I give you 3 similar cases before I do this one, so that similar cases which are actually useful. for our discussion. One is an ADS3, which is not R fourfold, but something close to it, which is a Calabi-Yau threefold times the two-sphere. This is the one studied by Maldacena, Strominger, and Witten, where they were studying M5 brane wrapped around holomorphic 4 cycles of a Calabi-Yau, and that gave a string. And this will give you a string which the near horizon geometry will have ADS3 times S2 times X3. So if you view this analog of would-be Calabi-Yau fourfold, instead replaced by S2 times X3, this is literally similar situation. Instead of holomorphic 4 cycles wrapped around the other one, we are doing special Lagrangian one. Otherwise, no difference. Similarly here, you could do the case where take ADS3 times X4, where now instead of M5 brane wrapped around special Lagrangian, you can wrap around holomorphic 4 cycles, very much similar to MSW. Or you can take ADS3 times X4, but now wrap it around special Lagrangian cycles. These are kind of like mirror to each other in the usual mirror symmetry sense, but anyhow, since we don't have mirror symmetry in M theory, it's just one lower dimension. It would have looked like mirror symmetry in type 2 language. So here, then, we can use anomaly inflow to say something about the central charges here. For example, for the case of A and B, the anomaly inflow, for example, in the context of MSW, fixes the central charge of the corresponding 2D conformal field theory by C right, C left being directly computable in terms of the triple intersection of the cycles in there. Actually, this is not that surprising because, after all, if you take a 4 cycle and rescale this 4 cycle number, you would expect it to grow like n cubed. And the reason is proportional to n cubed. And the reason is very simple, because if they weren't intersecting, you could separate them. And it would be sum of the linear one, because you can separate them. But if you try to separate them in their moduli, and if they intersect, then for each intersection, you could get extra degrees of freedom. And so therefore, the growth will be the triple proportional up to there could be linear terms, but other than that, there could be something proportional to intersection. And this agrees with the formula of MSW, which can also get by anomaly inflow. So this is not at all shocking. It's also explained in different ways. In the case B, the same thing as anomaly inflow. Now you get quadratic formula for the second intersection. And the reason is also not that shocking, because again, these are now 4 cycles inside a 4 complex manifold. You can try to deform it. And to the extent that you can deform it without intersecting, you will just get linear contribution to central charge. And to the extent that they intersect, you get additional contribution. And this is exactly consistent with these behaviors. So anyhow, the upshot of those 2 examples is that in one case, the central charge scales like cube, triple intersection, and the other one's quadratic in the case of 4 cycles. So now we come to the case of special Lagrangian one that we are interested in. And in that case, we have M5 branes on special Lagrangian 4 cycles. You can actually just compute the UV degrees of freedom on the special Lagrangian. And the special Lagrangian locally inside the Calabi-Yau has a geometry of cotangent of a Lagrangian 4 cycle. So that this is a good model for a local description of the neighborhood of the Calabi-Yau fourfold near the 4 cycle. And you can write down the left and the right degrees of freedom of the central charge. You get some central charge plus central left, central right is related to the Beatty numbers as well as the Euler axis of the L4. So in the case of the local Calabi-Yau, the self-intersection of it, and this is the key point, the self-intersection of the Lagrangian is the Euler characteristic of the Lagrangian. And so therefore, there's a bound here, but the self-intersection here is related to the F wedge F in the cancellation for the tadpole that we had, which is related to the Euler axis of Calabi-Yau. So this cannot be too big, the L4.L4. That is bounded precisely by Euler axis of Calabi-Yau times over 24. So you put these together, you learn that the central charge is bounded by constant order 1 times the Euler axis of the Calabi-Yau fourfold. In other words, you simply find that the central charges scale the way you would have naively thought, nothing fancy. Namely, for the ADS3 case, it scales like the Euler axis of the Calabi-Yau, at most or less, and the other one similarly like square. But there's actually a species scale. In other words, now I come back to Zohar's question. Suppose you have a Calabi with 10 billion or 10 to the 10 billion number of moduli. What about that? Well, then the scale of breaking of quantum gravity sets in much, much faster because there's a species scale. In other words, the Planck scale, the effective Planck scale is reduced from Planck scale by a huge factor corresponding to species scale. These are massless modes. I'm just saying the Calabi cohomology give you massless modes. Therefore, they will contribute to what is the effective Planck scale. And they will modify for you, they renormalize what you mean by the effective Planck scale. And they will be such that the species scale gives you a scale bigger than chi. In other words, the size of ADS is always smaller than the species scale in all these cases.
So the summary is that you're saying that there is no parametric regime.
No, there is no parametric regime.
But they might say maybe 900 as a, like...
No. I'm just saying there's no control over this contribution. No, they're talking about the Planckian situation, which therefore they cannot use effective field theory method for the next step. That's all. So in other words, even if there is an ADS, and I'm not saying there is no ADS, there might be ADS, Planckian ADS, like E8 type solutions that could very well exist. I'm not debating that. They'll be out of effective field theory control because of this idea. So that's the basic one. Now, you can actually say in the cases of orientifold type 2, which is the main case they did, because they were trying to do perturbative analysis of string theory. In that case, the bound is really minuscule because the upper bound and the corresponding tadpole is 250, again, for the known ones. And this, even if you ignore the species scale, is minuscule. So now you might ask, what happened to these papers who were claiming to get 10 to the, you remember, minus 120, you were asking me in the summer, what about that paper? You know what they did in this language? In this language, what they were doing, if you try to look at their flux, you can actually translate which brain would do that. They took a brain and anti-brain to cancel their tension to be 0 exactly, and then they look at subleading correction to get 10 to the minus 120. So the statement is that they would not find a supersymmetric vacuum. Now, they didn't compute Kähler correction, so they could not have claimed that they have actually found it. They only did the complex structure moduli. They stabilized there, but they didn't know how to compute the Kähler modular precisely, so they couldn't debate this question. But the claim is that they cannot find the Kähler stabilization because there is no supersymmetric brain in that class. So that's the problem with that constructions. Now, we have discussed this with these groups and other people who are pro-KKLT kind of things, and they ask what do they say? They say, how do you know that holography means you replace flux with brains? Well, this I find a little strange. It's like asking Andy and I, how do you know your black holes are represented by brains? Or in fact, even after the successful prediction that the black hole entropy works using brains, you could have said maybe there are other objects in gravity that have nothing to do with the things that we have discovered in string theory, which gives a higher or smaller central charge or entropy. Why not? That sounds like a tall order given what we have learned in string theory. And of course, if that's the case, that's much more interesting than KKLT or anything. We should figure out that. So anyhow, the burden of the proof will go to finding what such thing would be. So the conclusion is scale separation does not seem possible to achieve in ADS context, or at least if it is, it's going to be extremely tricky. We have found evidence against it. Assuming conventional holography, KKLT scenario is obstructed, I suggest we should be looking for other corners of the landscape if you are to obtain de Sitter or perhaps quasi de Sitter vacua. Thank you.
Additional questions. Okay.
So suppose that you can prove that scale separation is impossible. What does it imply? That we cannot describe using M theory and string theory nature, or what does it mean?
Well, there are two questions. One is we are talking about the ADS context. If that's what you're talking about. So in the ADS context, the question would be
most favorable.
Yeah. So the strongest version of let's restrict our attention to that one. It would be the question of whether or not conformal field theories, which are holographically realizable, could they have a big gap? If you can show that scale separation cannot happen, that basically means it cannot have parametrically big gap. Now, of course, you can refine what you mean by exactly scale separation and what's that A in that exponent. Is A is 1 or bigger than what powers we are calling scale separated. Typically, any A different from 1, we call the A less than 1, we call scale separated. People call it, even though they are now still somewhat correlated, but we say scale separated because relative to the dimensions, they can push up the dimensions. So then we would say that no holographic dual can realize big gaps in CFDs. That would be the answer to that question. Now, it doesn't prove that no CFD can exist with big gaps. It just means, at best, there's no holographic realization of them, which is the statement.
When you say parametrically, what exactly do you mean? You can mean several different things. One, there's a parameter which is smooth, and you can just dilate. The other, there's a parameter like 1 over n, which is not smooth, but you can make it arbitrarily small. And things are smooth in that parameter.
Yes.
And it could also be there's a parameter like 1 over n, but things are not smooth in n. So which of these three, so for the first one, where there's a continuous parameter, that's already known from the early 80s, mid 80s. Right, but this cannot happen for a continuous parameter.
Yeah, we're talking about discrete ones also.
There's that 1 over n.
Right.
There's a question of whether you do or do not need the assumption that the limit n going to infinity is smooth. I believe that for KKLT, they would like to argue that the limit is not smooth.
Well, right. No, they don't have. No, sorry. Let me just be clear. KKLT, we're not talking about DGKT. We're talking about KKLT, right? The KKLT does not have an n. KKLT just has a Calabi-Yau. So you're probably talking about DGKT.
Of Polchinski and others, where there was arbitrarily small parameter, but it came about by canceling other numbers, not by a parameter that you send.
Yeah, so there's no example of that type, which there's no example of that. The only one in the game is KKLT1, which is just a fixed set, finite set of Calabi-Yau. So you're looking for if the conjugate. It's almost not possible. Well, okay, so you say that, and I'm with you, but we are basically showing that it's parametrically means that Zohar's statement, like suppose we had a Calabi-Yau which was 10 to the 100 massless moduli. There's finite, 10 to the 100 is finite, and yeah, why is that not good enough? That's the kind of question that would ask. In that context,
I don't know if 10 to the 100 should be viewed as large or.
No, I think I would say people would consider it large. I would consider it large. No, I know, but this is what I mean by parametric. Maybe the wording I'm using is not the usual. Something which is natural units of one is parametric is huge. Okay, parametrically means compared to the typical ones is much bigger. That's all. I think it's not a precise math term. I agree, but.
I shouldn't go there, but. When you just discuss a number,
right?
Why should you compare to 1?
No. You wanted I would say it because in the holographic dual ones, you want the lambda to be much compared to the Planck scale, lambda in Planck unit close to 0. That's what I mean. This is related to the same statement. Yeah. That's what I mean.
Okay. More questions? Okay. If no, let us thank.
Thank you.